Hi, in this video, we will discuss how to find the center of mass by using the integration. This application is under the proper integral. To find the center of mass, we need the understanding of moment. And you should know the difference between the moment and the torque. In simple, a moment is a measure of its tendency that causes a body to rotate about a specific point or axis, and it can be computed by using this formula. You can go to the appendix to find the difference between torque and moment here. We use the symbol m here to represent the moment or the moment of force, and we use the symbol tau here to represent the torque. Although they are using the same formula, which is the displacement multiplied with the force, moment and the torque are not the same thing. Moment is used in the static analysis where the structure is in equilibrium. For example, in this case, you can see there is one cantilever beam under the force 100 Newton in the end of the tip here. Force multiplied with the distance here give you the moment. So if you have the force in this direction, the structure tends to rotate in this direction. This rotation tendency is due to the moment. However, in actual, it's just tendency. There is no rotation happen in actual because the beam is fixed in this direction where we have the counter reaction moment here. So the beam does not rotate due to the moment in this case and is static case. On the other hand, torque is used for dynamic or the kinematic case. Torque will cause rotation to happen in actual. For example, when you turn the screw by using the screwdriver here, so you are actually applying a rotation force here, which is known as torque. So the screw will be rotate and move. In this case, two kids are playing the seesaw here, where you can see this kid apply the torque in this direction to make the seesaw to rotate in such position. To determine the direction of the torque here, we need to draw the XYZ axis. So in this case, you can see that the direction of the torque is in clockwise of the y-axis. Therefore, we say that the torque is in negative y-axis. So you can see that these two kids are playing the seesaw also, and the kid here apply the torque such a way that it rotates in this direction. So the torque is applied counterclockwise to the y-axis. Therefore, the torque is in positive y direction. So the way to find the direction for the torque and moment are the same. So basically, this is provided for you to understand clearly how to find the direction for moment later on. Center of mass can be thought as a balance point where the whole body mass appears to be concentrated, and the force acting at this center of mass will not cause rotation. You can use your finger as the pivot to support the item. So if you put the finger at non-center of mass for this item, the item will rotate and unbalance. This guy here is trying to find the center of mass for this item. So you can see the center of mass is around here, where when you put the finger over here as the pivot, so in this case, the item will be balanced and there is no rotation. Let the total mass on the left hand side to be m1, total mass on the right hand side to be m2, and you have the fulcrum here. Let the 3D axis to be this, so that you have the x-axis only, and you have the x1 coordinate here for the m1 and x2 coordinate for the m2, and x bar here indicate the center of mass position. So the fulcrum here must be positioned in such a way that the moment here due to the mass 1 will be equal to the moment due to the mass 2 here, so that the total summation of moment will be equal to 0. So in this case, it will be equilibrium and the fulcrum is located at the center of mass. Since the moment due to the mass 1 has the clockwise rotation with respect to y-axis, therefore you can write it to be negative my, where the moment can be computed by using this formula, distance multiplied with the force. So in this case, the force is due to the gravity, where you can obtain the force equal to m1g. And then the distance is measured from here, which is equal to d1. Therefore, you obtain the moment for the mass 1 equal to negative m1g, which is the force, multiplied with the distance in the x direction. So this should be dx1. There is a typo here. Negative here should be due to the clockwise with respect to the y-axis. You can continue to find the moment due to the mass 2 here, where you can see the direction is counterclockwise to the y-axis here. Therefore, counterclockwise to the y-axis, you should obtain positive. So please correct this. This should be counterclockwise. Then the magnitude of the moment is equal to the mass 2 multiplied with g, which is this, and then you multiply with the distance here, which is the distance dx2. So you can continue to find the distance here between these 2 points by using the coordinates here. So you can take the square root of the x bar minus x1 here, and then you take the square plus the y bar minus with the y1 here, power of 2 plus the z bar minus with z1 here, power of 2. Then you should obtain this equal to the x bar minus x1. Since the information for the y and z here are all 0, therefore this can be cancelled. And the square root here can be cancelled with the square, and you should obtain this answer. So you can find the distance dx2, which is this, by using these 2 points. Similarly, the y and z information are 0, substitute inside this formula, so you can cancel the square root and square here to obtain this answer. So in this system, you have moment 1 and moment 2. So the equation is given here for moment 1 and moment 2. Take the summation of all the moment 1 and moment 2 here. Then you will find that the negative can be moved to the right hand side, and you should obtain this. Then you can substitute the dx1 and dx2 inside this formula to obtain this equation. Since we want to find the center of mass, which is at the point x bar, therefore we put this term to our left hand side, and then the rest we put at the right hand side. So you further derive this. To take the x bar, you divide it with the m1 plus m2. And from here you know that the total mass of this item is equal to m1 plus m2. So this is the final formulation to find the center of mass at x bar. So this formula is used to find the center of mass when you have 2 discrete mass on it. But in actual scenario, you may have n number of mass. For example, mass 1, mass 2, mass 3, 4, 5, 6, 7, and so on. To find the center of mass for this situation, we can extend the previous formula into this, where you can see that the summation of mass multiplied with the distance can be written into this form, and the summation of the mass can be written in this. So in simple, we can say that the center of mass at the x coordinate is equal to the moment about the y-axis divided with the total mass. We can extend the center of mass problem for 1D to the 2D cases here, where you can see that the formula to find the x bar is still remain the same. And you have a similar formula to find the y bar. So for the 2D case, you have your y-axis and x-axis here, where you have 3 masses in this example. So if you take the mass multiply with the s distance here, then you get the moment that has the tendency to rotate about y-axis here. So if you plot the mass tree and the distance x3 in this 3-dimension graph here, you will see that the mass tree will exert a force going down, and the force multiplied with the x3 will cause the moment to rotate about the clockwise of the y-axis. So if you look at the M1 here, where the force is acting down, so this is the distance x1. Take the x1 multiplied with m1, give you the moment in this direction, which is counterclockwise about the y-axis. So you can continue for the mass 2, which is located here. The force is acting down, and this is the distance x2. So m2 x2 give you the moment rotate in this direction. So all of this moment here, you can take the summation in this form. And if you divide it with the total mass, mass 1, mass 2 plus mass 3 in this case, then you obtain the x bar. If you take the m1 and multiply with the y1 distance here, then you obtain the moment in this direction, which is clockwise to the x-axis. So you can see that when you take the mass multiplied with the y here, you are actually computing the moment about the x-axis. So this one, I draw it wrongly. It should be located here. So m2 multiplied with the y2 here, then you obtain the moment rotate in counterclockwise with respect to the x-axis. So for the mass 3 multiplied with the y3 here, then you obtain the moment in this direction. So take the summation of all the my here, which give you this result. So this is in the moment about x-axis, and divide it with the total mass. Then you obtain the center of mass at y coordinate, which is the y bar. Assume that after you perform the calculation, you obtain the x bar equal to 1, y bar equal to 3. So you can see that in this graph, let's say 1 is here, and then 3 is around here. So this is the center of mass, which is 1, 3. So imagine that you put your finger to support this object that has the concentrate mass as the mass 1, mass 2 and mass 3 here. So if you support at the center of mass here, then you can balance this object. Center of mass is equal to the centroid when the density is constant, and is also equal to the center of gravity if the gravitational field is uniform. For a regular shaped object, we can find the center of mass easily by using either the formula or graphical method here. If you want to find the center of mass for irregular shaped object like this one in black color, so in this case it requires some integration technique. To find the center of mass for this black object, first of all you need to define the y function here. So let the y equal to fx function here. Then you need to know the lower limit and upper limit, which is a and b. So in this case, is a constant function here. Therefore, your y equal to gx is at x-axis. Previously, we know that the center of mass for the x-coordinate and y-coordinate can be given by these two formulas. So if you want to find the x-coordinate for the center of mass, then you can take the moment about y-axis and divide it with the mass. Assume that you have a very small element located on this irregular shaped item where the delta x here approaching 0. So in this case, if you want to find the mass for this small element, we can obtain it by using this formula where we know the mass is equal to rho v. So I here indicate infinity rectangular bar from the limit a to b. So your I is approaching infinity when the step size, which is the delta x, approaching the 0. In this case, we have a 2D problem. Therefore, your volume is equal to area multiplied with the thickness. We can assume the thickness equal to 1 for 3D problem. Therefore, you obtain the volume is equal to the area in this case. And we can further reduce the area equal to the height multiply the width. So let's look at this rectangular bar. So the height is the fx function and the width here is delta x. Therefore, you can substitute it inside. So you know that this formula is to compute a mass at I element, and you know that I element is approaching infinity where your delta x is approaching to 0. So if you want to know the total mass for this irregular shape item, then you need to integrate from A to B, like this. And then rho is a constant, which is the density. Therefore, you can take the constant out and multiply with the fx function. If the delta x approaching 0, so in this case, your delta x can be written in dx. So this formula can be used to compute the mass. Let's continue to find the moment about the y-axis, which is equal to mx bar. So you can write my equal to mx bar. So you can see in this case, the center of mass of this rectangular bar is located at the xi bar here, and this height is half of the total height, where you can see the height here is fxi bar, then half of the height here, and this is the place for the center of mass. So previously we learned that the mass can be equal to the rho v, where the volume, after you assume the thickness equal to 1 due to the 2D case, then you can have the area. So the area can be further reduced to the height multiplied with the width. So this is the moment about y-axis for this I element only. To know the total moment about y-axis from A to B, you need to perform the integration. So the moment about y-axis is equal to the integration of the rho x fx dx, which is this. Lastly, let's find the moment about x-axis, which is equal to the mass multiplied with y bar. So y bar is the center of mass at the y-axis. So for this simple structure here, which is the rectangular bar, so the y bar is actually just half of the height, which is equal to half fxi bar. So you can substitute this inside, then you should obtain this, and the mass is equal to rho v here. So you can further reduce the volume into the area only by assuming the thickness equal to 1. And the area can be further reduced to this, which is the height multiplied with the width. So you can see that we can multiply fx, okay, to obtain fx squared here. So this is for I element. So if you want to take the summation of all the total moment about the x-axis from A to B, then you need to perform the integration. So you need to integrate half multiplied with the rho fx squared and dx. So with that, you obtain this integration. Lastly, since the density is constant for this object, then we can further simplify it, and the rho here can be cancelled to give this final answer. So this is the formula to compute the x bar and y bar, which is the center of mass for this irregular shape object. The easy way to remember these two formulas is to recognize the bottom part here is the area under the curve. Let's say you have the function fx. If you integrate from a to b, you're actually computing the area under the curve. So you can see at the top there, you also have the fx function. Just that if you want to find the center of mass at the x coordinate, then you need to multiply with x. But if you want to find the center of mass at the y coordinate, you need to multiply with half of the fx by knowing that the center of mass at the x coordinate is still x, but the center of mass at the y coordinate is half of the fx function. So if you remember this, then it will be easier for you to remember the formula for x bar and y bar. Let's apply the formula here to find the center of mass for this object. And you can see that the function here is given y equal to 2 sine 2x. So if you want to find the center of mass for this object in green color, we need to solve three integrations. So for the first integration here is the area under the curve, which is this. So you can substitute the fx function, which is the 2 sine 2x inside, and the limit is from 0 to pi over 2 here. So after you integrate this, you should obtain 2. To find the x coordinate for the center of mass, then you need to multiply the area with the x. So this is the second integration. So you can see that you have the area integration and you need to multiply it with x. So from here you can use the integration by part to compute the integration. So you should obtain pi over 2. To find the y coordinate for the center of mass, remember you need to multiply half of the fx function to the area. Therefore you obtain half fx squared here. So we multiply the fx by square and then you have the half constant here. To solve this, you should obtain the answer to be pi over 2. And simplify the answer, you obtain the x bar and y bar equal to pi over 4. So if you draw it, let's say this is your x bar at pi over 4. Over here is pi over 4, which is your y bar. Therefore, this is the center of mass for this green object. How if you have a more complicated object and you want to find the center of mass for this item? So in previous case, you have the y equal to gx at the x-axis. So we know that x-axis is equal to y equal to 0. So previously you have the gx function equal to 0. However, in this case, your gx function is a curve like this and is no longer 0. So you can see the general formula here where we know that x bar and y bar so is equal to x multiplied with the fx and divide with area. So in previous case your gx is equal to 0. But for this case your gx is no longer 0. So you need to use this general formula to solve the problem. And your area previously is only fx. So in this case you need to minus with gx. So previously it can be equal to fx only because the gx is 0. Right? So y bar here, you can see previously you have half fx squared. Now since you have gx, you need to minus gx squared. So this is the formula. Let's use this formula to find the center of mass for this item. So you can see that you have two functions here to define this item. So here is your fx and here is your gx function. So first of all, we need to find the area for this region. The area here is equal to the integration of fx function minus with gx function. So you can substitute the fx function here, then you should obtain this, and substitute the gx function here, and solve it, then you should obtain the result. So you can see this is also area, therefore you obtain the same result here. And to find the x coordinate for the center of mass here, you need to multiply the same area formula with the x. Therefore you can see this term and this term area, they are the same, and you need to multiply x to find the x bar. So solve this integration, you should obtain this result, and you continue to find the y bar. So for the y bar, you have half multiplied with your fx squared, and this is your gx squared. So after you solve this, you should obtain this answer. So you can further simplify the calculation, and after that you can plot it. Over here you have around 12 over 25 for the x bar, and over here you have around 3 over 6. It's 7. So this is the center of mass. This is for your extra information. So there is a relationship between the surface area or the volume of revolution with the centroid. In the Pappus' first theorem, it suggests an alternative way to compute the area of revolution by using the product of the s, which is the arc length, multiplied with the distance traveled by the centroid. So you can see that in this case you have the arc length equal to c. So here you have the arc length equal to c, and in this case the arc length is in semicircle, which is also equal to c. So for the semicircle, we know that the half circumference is equal to pi multiplied with radius. So you can see there is a triangle shape here, so you can find the arc length, which is the c, by using this formula. So your c is equal to square root of this. So you can obtain the arc length easily, which is equal to c value for these 3 different arc lengths in blue color. Then you need to find the centroid for the arc length, which is located at here, here, and here. So the gray color here is the axis of rotation. Therefore, you need to rotate the centroid by 360 degrees. With that, this is the distance, which can be computed by 2 pi a. Similarly, you can rotate the centroid and compute the distance by 2 pi a for these cases, where the a is the distance between the centroid to the axis of revolution. With that, you can obtain the surface area for these 3 geometry is equal to the arc length, which is the c here, and you can draw it like this, and multiply with the distance traveled by the centroid. So you know the centroid for this arc length, and then you rotate it with 360 degree with respect to the axis of rotation here. So by doing this, the distance of the revolution here is equal to 2 pi a. So you can see that the area can be computed by using this formula. We can use this formula to find the surface area for this object. So in this case, you need to identify the arc length. So let's say this is our arc length. So we can obtain the arc length by using this formula, which is 2 pi r. So you can see that the radius here is identified as small letter r. So you can find the circumference, and circumference is the arc length. And then you need to identify the centroid for this arc length, which is located at the center here. So you need to travel and rotate it by 360 degrees with respect to the axis of rotation here. to form this object, right? Therefore, you can obtain the distance traveled by the centroid to be this is equal to 2 pi multiplied with capital R. So this is the distance. So after you multiply it, you obtain the surface area. In the second theorem, we can use this formula to find the volume. For example, in this case, the area of this space can be computed by using pi r squared, where the r is in small letter. So this is the area here. Then the distance here is the same like you compute previously, which is the centroid of this area, and you rotate it with 360 degrees to form the volume of this object. Therefore, you successfully obtain the final answer for the volume computed by this product.